Hello. Hello, everyone, and welcome to yet another webinar of OPCUAFX professionals. And I'm going to wait for another couple of minutes for people to join. And meanwhile, as you know, this is OPCUAFX Part 5 webinar, and it's about, today we are going to discuss about achieving real-time Ethernet performance using OPCUAFX. So first we will go through an overview, and then we will see the concepts which is going to let us achieve this, and then we are going to see a quick demo about how TSN is helping to achieve the real-time Ethernet performance. So if you're going to be this is going to be your first time at this webinar series, and please do consider joining the OPCUAFX professionals group. So we have a YouTube channel and also a LinkedIn channel. So this particular initiative is done by B&R Automation and part of Schneider Electric, and also along with Utunga. So I'm Melvin Francis from BE.services. I'm the technical marketing manager here, and I take care of OPCA plus TSN, which is OPCUAFX related activities happening at our company. So if you're new to this webinar, I would recommend you to go through this OPCUAFX professionals YouTube channel, so you could see so this is part 5. So I would recommend you to go through part 1, part 2, and also we had a great event at SPS last year happening at Nuremberg. So we had an event, and we have some recordings from that event, and also the previous webinars as well. So I will just give another minute before I'm starting to make sure that everybody interested has joined the meeting. So this is going to be an interactive webinar. So this is going to be an interactive webinar. So please do drop in your comments, and I will be able to see in the comments. And if you have any questions, please do drop in so that I could also answer to your questions on the go as well. Yeah. Okay. So am I audible? So can somebody put in a comment saying that audible, so that I could start in another few seconds? Just to want to receive some feedback from the audience. Okay. Yeah, so let me start with the presentation. So first of all, thanks for everybody who joined this webinar. And today we are going to see how to achieving real-time Ethernet performance using OPCUAFX. And as I think many of y'all know OPCUA as a protocol for a long time, and this UAFX addition on top of it gives a whole new meaning to the standard. And also we are going to see like how we are going to achieve real-time Ethernet performance using the OPCUAFX standards. And OPCUAFX overview, this is an extension of OPCUA designed for field level communication and standardizes the data exchange between controllers, sensors, actuators, and machines. And why it is important? Because it enables seamless interoperability. Interoperability has always been a problem in industrial Ethernet standards, and also support for real-time communication, and also sensor to cloud communications, and also controller to controller communication. This has always been a bottleneck for the legacy Ethernet standards. And also when we are scaling from small devices to large industrial networks, we would need multiple protocols, but OPCUAFX itself gives you a proper framework that would enable us to achieve these requirements of Industry 4.0 standards. The key features involve standardized information models, and this is not like any XYZ person written. This is based on a proper standardized information model, and it supports it goes well along with time sensitive networking, which is the topic for today, which enables deterministic low latency communication. And also UAFX gives you the capability of plug and produce. Since we are all going to be interoperable, we're going to speak the same language, so this plug and produce is possible. And obviously safety and security is also part of it, and there is major concentration, and also the support for the standard to achieve the necessary secure and safe way of operation is possible. And easy integration with IT and cloud connects factory floor devices with edge computing and cloud services. So how this is going to be possible is from this slide. You can see the various communication protocols that is supported by UAFX. So you can see that there is GPTP, LLDP, NetConf, which are network management kind of communication layer protocols. So here GPTP promises for time sync, LLDP for link layer display, and also NetConf for network remote management. So for example, for configuration and stuff like that. And for communications, we have client server communications and pub sub communication here. So these combination would help us to realize all realize both real time uh, kind of communication, and also if you have service kind of communication, or if you have configuration, all this is possible with these standards that you saw in the previous slide. So when we say OPCUA, I think most of y'all would have understood OPCUA as a client server communication model, and you would have obviously tested here. And for example, imagine there is a device like a factory floor device with a robotic arm and a controller. So imagine it is like motor position, motor speed, and a homing position are the three variables that are available here. So I think most of y'all would have had experience to access it using a client, come into the server, either read, write, monitor these variables, or even subscribe to them so that you continuously monitor them and visualize them. And I think these kind of exercises would have been quite familiar. But what is the power of OPCUA, or what OPCUA UFX defines, is that there are different transport layer protocols which would support you to, for example, if you want the motor's position to be controlled in a way like controller to device, then we could go for PubSub over raw Ethernet, where the cycle time is less than anything like 250 microseconds or 100 microseconds kind of cycle time, which is high speed and highly deterministic requirements are there. So this can be possible by PubSub over raw Ethernet. And we can also use PubSub over UDP. So when you are having controller to controller communication, and if the network requirement is 1 millisecond, then anything above 1 millisecond, so this particular transport layer protocol would be quite helpful for us. And if you want to send this data to cloud, you can just use PubSub over MQTT in a secure way. In network layer security, transport layer security, and user level security can be achieved, and you can push the data from your factory floor to the cloud. Imagine examples would be Azure or AWS cloud applications can be sent directly using MQTT. So this is where I would say a typical use case of sensor to cloud communication, and everything is done by single protocol, as you can see here. So this gives you the possibility to achieve sensor to cloud, cloud to compute, even satellites, mobile robots. So all that you can see here is possible. So exclusively today, we are going to see this particular circle, which is the field level communications, that is OPCUA FX, which means field level communications. So here you can see controller to controller is happening, and controller to device communication is happening using OPCUA PubSub. OPCUA client server helps you for configuration, management, network management, and things like that. So to give you an overall technical aspect, like what all UAFX is comprised of. So you can see that for real-time Ethernet communication, we are using the TSN time-sensitive networking. So for this, we would need GPTP, LLDP, QBB, QBU, and then on top of it, we would need a networking stack, and we would need a OPCUA server, which does the client server communication, and also OPCUA, which does the publisher and subscriber on top of it. And so for UAFX, there are information facets, information model facets that you need to support, an automation component, and also we need to support the configuration and engineering. So this entire pieces of software that you're seeing together combined comprises of UAFX, and as per our network requirements, quality of service, and if it is going to be a controller device at or at which level at you're staying, so we need to alter this and configure this SDK to make it work for our specific requirements. So now that you have seen so many technical items or technical jargon, so it might be confusing. So in the upcoming slide, I would show you a simple demonstration which would help you to visualize how UAFX controller to controller communication works. So here you can see we are using a BNR automation PC that you're seeing from the architecture network diagram here. So this particular automation PC sends in the robot position data, the position that it needs to trace the path. So we have used a Neura robot here, which collects the data from the automation PC and also sends it feedback to the automation PC so that the numerical calculations would happen here. So here it is a typical use case of UAFX controller to controller communication, where the overall cycle time is at 1 millisecond and the robot should receive the packets. So every 1 millisecond, it needs to get a packet. So it means that the jitter should be in plus or minus 20 microsecond level, and also that also there are other traffic that are available in this network, and they should not disturb the packets that you're seeing here. So it means that, imagine if you are going for industry 4.0 kind of use cases, there will be robot data, and also you will have audio video data from your CCTV or your net or your ERP kind of solution kind of data, all involving together, and that should not rupture the traffic that is really controlling the robot here. So this is what we are saying, deterministic Ethernet communication, and we will see how TSN is going to help here, and how we can see UAFX is able to work alongside of other traffics that are available in the network as well. So this is a quick controller to controller kind of example. And in the next example, you can see this is like a proof of concept where we can see one controller controlling two devices, which is doing a motor position kind of a demonstration here. So here, this particular controller sends the position values through the TSN switch that you're seeing on the screen. And then both of these devices receive these packets on time without much jitter, so that you could see a seamless movement of the motor movements, motion control happening here. Okay, so now from this network diagram, you could see that there are totally 1, 2, 3, 4 devices involved, and all these 4 devices are in time synchronization, and they are all in time accuracy of plus or minus 20 nanoseconds, and even sometimes less than that as well. So when you are saying that we could reach microseconds type of synchronization, this gives you the capability to reach different level of synchronization between the devices and the controllers that you're seeing here. So now that I've used TSN multiple times, so it would be hard for anyone new to understand. So let me give you a quick example of how you can see the TSN as, and I could give you a real world example of how TSN works, and this would give you a clear picture. And please do comment down if you have any questions so far. And so let us take a meeting room example. So imagine there are 8 people in the meeting room, and everybody has important information to talk, but everybody are talking at the same time. So what happens is person 1 talks, and also person 6 talks, and there is a lot of chaos in the in the meeting room, and there is a lot of information that is being dropped off. So for a solution, what happens is everybody comes together, and then they decide, like, let us choose one person as the grandmaster, or the master, so that he is going to say share his clock time to everybody. So to solve this problem, what they are planning to do is they are choosing one person, and his clock is going to be the grandmaster clock, and everybody else are planning to synchronize according to him. So imagine if I am like 2 minutes later to him, I'm adjusting the clock to one step back so that I'm able to match his time. And if I'm backward to them, I'm going to make my clock ahead, and I'm going to make sure that front and back I talk to the grandmaster, and I'm keeping my clock always same to him. And now all the 8 people in the room are in plus or minus less than 1 microsecond of cycle time, less 1 microsecond of accuracy. So now that this is achieved, now everybody comes together and says, when person zero talks, nobody else should talk. If person one talks, person two has to wait for a slot, and similarly it goes through that. So here you can see that there are totally 8 people here, and they have split the entire time into 10-second slots, so that when one person speaks, the other person has to wait. So even though, if imagine if person one has information that he needs to talk for 30 seconds, he has to wait for 3 cycles to complete his information, so that nobody's information is falling here. So just to have a quick overview, so there was a lot of problems, like everybody were talking together, and now that they all synchronized their clock to the grandmaster clock, so that they are in plus or minus less than 1 microsecond of accuracy. And then what they have decided is they are going to have cycles, so everybody gets their own um, time slot to talk. So this is where we could say at this point everybody has reached 802.1 as kind of accuracy. And here everybody have their own slots, and this is equivalent to 802.1 QBV, where you can see when all the 8 people were talking, so replacing 8 people with 8 traffic classes. So in an industrial automation network, there would be 8 different types of traffic classes. So for example, there is going to be real-time data, there's going to be isonchronous data, audio video data, which comes from the CCTV, and there's going to be voice over IP, control data, and also configuration data and service data. So these kind of the different traffic classes are going to be on the same wire, and this is what happens when all of them are going to talk at the same time. So replacing 8 people with 8 traffic classes, when QBV is switched off, this is how you're going to have the network where there are going to be a lot of losses. So imagine your robot important data is going to be dropped because some random CCTV footage data collided with it and the packet has been dropped. So that is going to be not real time, and it is going to create a lot of problems it is going to when your isynchronous data is falling off. So now you can see that everybody in the network are in time synchronized, and we have a proper scheduling of traffic. So here you could see 8 type of traffic classes, everybody are getting their own time slots. So I've split I've here in this example I have provided like 125 micros, so this is like 1000 microsecond cycle time, and each of them are getting 125 microseconds of cycle time, and each traffic class is given the equal bandwidth. Now, coming to a real-time scenario, how we can make sure that the robot does not drop any of the data is, if my robot data is going to be coming with a VLAN tag of so replacing 8 people with 8 traffic classes, and each traffic class can be differentiated with the VLAN tags, and VLAN tags has something called as priority code point. I think I am giving a lot of technical data, but this is a huge topic. But for us to understand, I hope this example helps you to realize like how the things happen on a wire, on a switch, or on an end device. So what we could do is we could allocate more time for isochronous traffic and lesser bandwidth for your CCTV or for your control data, for your configuration data, or any other low QoS kind of information can be put into a separate slot. So So now coming to the next complicated topic. So now that we have learned what time synchronization is and what is scheduled traffic, now let us come to an example of what is frame preemption. So imagine person number 3 is talking. So in our example, the person number 3 is going to talk for 10 seconds, but person number 4 has much more important information and he needs to stop him so that the important information passes through the network. So what he can do is, so we can mark person number 4 as an important moderator, so he can come and tell the person number 3 that, hey, you need to stop talking, keep your rest of your so I know that you have 0 to 10 seconds, but I cannot wait for another 15 seconds time. So what he does is he interrupts the person at the 10-second time. He gives in the small bit of information that is needed inside the network, and then he exits, and he gives back the control to person number 3 so that he continues to transmit the information that he wants to do. So imagine, so just replace this information into a huge packet, but the huge packet cannot make the packet the important packet to wait for its entire transmission. So when it is being cut, then he could cut at some point of time and give back the control to person number 3 so that he could transmit. Yeah, so let me. Yeah, that's a good question, Felix. So the scheduling is not configured automatically. You need to do it by, we need to do it manually. And we are going to see in the demo, like how we are going to do manually. That's a very good question. Thanks. Yeah, so when somebody interacts, it feels really good, or else it looks like I'm talking to a wall. Thank you. Yeah. So what are the TSN standards? So TSN is comprised of set of IEEE 802.1 standards. So you can see .1A is QBU, QBV, QBU. So these are the three things that we saw today. And also there is forwarding and queuing, enhancements, path control, per stream filtering, seamless redundancy. So these are the collection of TSN standards. But out of them, so which standards are mandatory? So according to IEEE IEC 60802, so these are the four standards that are mandatory, and also CB, which is seamless redundancy, as we saw already. So why TSN is necessary for IT and OT convergence? So as I already gave an example, so when there are 8 different types of traffics available on your network, so when somebody says IT and OT convergence, we always think about as how do you get your data and you push it to the cloud. So this is what we normally think as IT and OT convergence. So if you have a very good edge gateway, or you could do PubSub over MQTT, or you could do REST calls, there are different methods where you can send your data from factory floor to the cloud. I would say the best method is OPCUA, but still there is problem if you don't have your your network layer configured properly. So imagine you have a lot. So when you introduce your so to push your data from your factory floor to the cloud, you obviously would need an active internet connection, and there can be different types of uh, traffic that is available on the network. So that's what you're seeing on the left. So even when you have realized that you could push the data from your sensor to the cloud, but still, if all of them are going to comprise on the same wire, then it is going to be a chaos if there is no proper scheduling, as you're going to see here. There is going to be interruption to your real-time data, and uh, if the jitter is more, or if the packet has been dropped due to collision, or if the packet is not delivered on time, and there is chaos is going to happen. So let me give you a much more simpler example that would connect to everybody. So if you take a car, the airbag data is the most important data, because if the information from the sensor, the collision sensor, is not passing through the airbag open, and there is severe consequences that we need to face. So this is where we need to compare it, like the car infotainment data can wait, or it can have lesser QoS, quality of service, but the airbag data has to be delivered on time, or else there is going to be a lot of problem. So how do you combine these both networks? Without TSN, whatever you see on the left side would happen, even though on the right side we could see that there is proper there is proper time synchronization, there is proper bandwidth allocation, and there is seamless redundancy, and there is frame preemption. This makes sure that our entire network is working in a deterministic fashion. So this is how the network jitter looks like in the robot example that I showed previously. So this here you can see that the jitter of the packet is plus or minus 5 microseconds. So what does this graph means? So imagine that I need to send one control data every 1 millisecond. So the first packet will come at 1 millisecond, second at 2, 3, 4. So for imagine when it reaches should reach at 3 millisecond, it could not be like 3.5 milliseconds. It should be just 3 milliseconds plus 5 microseconds or minus 5 microseconds, and the network should be in that level of determinism to achieve a motion control application or a process control application or image recognition application. So it should be the transfer of data should be of this level of network jitter should happen. So a quick overview about how what is the round trip time that we were able to achieve. So here you could see that we have a Linux controller that sends through the TSN switch, and the end device receives the packet. And if you send back the packet, the overall loop takes, if the running cycle time is at 1 millisecond, with OPCUA publisher subscriber plus TSN, we are able to achieve a round trip time of 2 milliseconds at 1 millisecond cycle time. So it takes like 2 milliseconds for a packet to go here. You increment the value and then you get it back. So this entire loop uh, uh, measures like 2 milliseconds, which is like 2 times the cycle time. So this would raise a lot of questions. So please do DM me if you want to understand more. I think if I would like to go deep into these details, it would take a lot of time, which is out of scope of this webinar. So deep dive a bit more details into what 802.1 AS time synchronization is. So in the first example, we said there is in the meeting room of 8 people, there is going to be one guy who's considered as the master, and he's going to send his clock time to everybody else so that all the other slaves can twist their timepiece and be accurate to them. So for people, it's easier, but for machines, you need to have a protocol, and this is being defined by 802.1 AS, which is called as a PTP implementation. So here you can see the master sends a sync message and then a follow-up message. This is where he sends his clock and then asks the slave to adjust his time, and then he sends the slave sends back a delay request, and then again the delay response message is received. So now you have T1, T2, T3, T4. So with this, you could say like, what is your offset to the master, and the slave would be able to control its time effectively. So this is like a whole big topic, and I just explained it in 20 seconds. I don't make justice to it, but it would go outside the context of this webinar. And also, you might also have a question like, who's going to be the master? What if all the 8 people are equally important? And for this particular confusion, there is going to be the BMCA algorithm, best master clock algorithm, which decides like who's going to be the master. So it has its own parameters, and according to the parameters, out of the participants in the network, this particular grandmaster is being chosen, and it does the necessary transactions to get it completed. And yeah, so we are going to go to the demo section now. So we will see how things are going to work, and then we will come back to this slide, the migration from OPCUA to OPCUA FX. So I hope I was audible. If somebody could give me a message, it would be great, so that I could go to the next phase of showing a quick demonstration about how time synchronization and traffic scheduling works. Okay. So whatever you're seeing on my screen is a live demo that is running now, which is on or right of me. So I was not able to bring this demonstrator to the screen, but you could see like I have logged it to my local PC and I'm running this. So this particular test suite is called the ETSN test suite, which comes part of our ETSN SDK, which we'll see the fine details a bit later. So we have two devices. So what I'm showing here is exactly this setup is what is running on to my right here. So there is a Linux device, there is a TSN switch, and there is an end device. And what we are doing is we have injected a lot of traffic, and also we are running the PubSub traffic internally, and still the demos running here. So you could see there are 8 types of traffic classes that are running here, and each one is having a different color here. And now there is chaos, as you can already imagined. So there is no time synchronization. There is no um, uh, there is no 802.1 QBV enabled on the switch. So what we are going to do now is to first start the time synchronization between the Linux device and the switch and to the end device. So you could see that I have started here. One second, I want to show something else as well. So in this demonstration, we are using a Moxa switch. It's a 4-port Ethernet switch that is currently running now. And here, let me show the time synchronization status. So I am doing all this monitoring on port number 4. So whatever we saw here is the monitoring that happens on port number 4. So here on the port number 4, first of all, there is no synchronization that is available. So imagine port number 4 as connected here to the Linux box. And I'm going to start the time synchronization now. So what happens is the there is 802.1a is happening. The PTP protocol takes care of. So you could see the packets are being sent here, and they have decided that the master is going to be the switch. So you can see that port number 4 is the master, and the port that is connected here is time sync capable. And RMS means like what is the master offset. So the offset, first it was big, and then slowly they negotiated between each other, and then now they are in plus or now they are in the level. So this is the offset, and now they started with 2200 nanoseconds, and now they are in the level of plus or minus 5 nanoseconds, which is really good. And then you can see the neighbor propagation delay is 29 nanoseconds. And yeah, so just to show that how it works, so if I close it now, you could see that you could see this particular port is not they are not synchronized. You could see it went back to no. It will remain to no until I start the PTP protocol on the Linux box that is available here. So once I start it, you could see that they have come into synchronization, and still the traffic looks pretty bad here. So I hope you understand why, is because we have not yet enabled QBV now, which is the which is the traffic scheduling. So now what I've done here is you could see the port status of port number 4. It is not enabled, and now we are going to enable it now. And this is how the port status would look like. So since it is a very basic demonstration, what I have done is I have allocated equal bandwidth for each of the traffic that is available here. So what kind of traffic I'm sending is we are sending equal amount of traffic for each traffic class, which you could see like they are just UDP packets marked with. If you want more details, please do direct message me. You can see there is a lot of traffic being pushed into the network. So that's what you're seeing in different colors here. So let us wait for some time. So now that we know that 802.1 QBV is also enabled, and now the switch is going to prioritize all the traffic, and you can see the graph is going to slowly change. This is not like very real. This is real time denotion of what is happening on the network, but it needs some time to refresh the old packet. So it's like every 1 minute it's going to change. So if now somebody has questions, okay, first let me answer Felix's question. Meanwhile, during our wait time, so this is how I'm configuring my network. So let me give you an example. If I think if I think that Q0 needs more time, I could say the slot could go up to 250 microseconds. So it starts from 0 here and comes till 250 now. Previously it was just 125. So I need to know my network requirements, and then I need to do it manually here, or use a configuration tool or a centralized configuration tool to do it. So did this answer your question, Felix? I hope this was self-explanatory, but if you still have that question, please do let me know. So now you can see slowly the traffics are behaving to our gate control list. So this particular gate control list is like every traffic class is going to take equal amount of interval, and slowly you could see that they have come back to their planned level of bandwidths that we allocated in this particular gate control list. And also the synchronization between the Linux device and the switch is in the level of nanoseconds. So even if this fails, then you would not achieve this. I know it's pretty hard to understand, but please do reach out to us, reach out to us, and reach out to me. We could discuss more if this sounds interesting to you. So the blue is where we are going to put in our robot. The blue traffic is where we are with priority code point 3 is where we have put in all our robot data, or for a generic audience, this could be the airbag data, which I try to explain it in a quick way. Yeah. So any questions here, please do let me know. I'm going to finish my demonstration here. And also for few people who wants to know what would happen if okay, let me see the question. The time synchronization is done by network card of my controller if it supports 802.2 and is managed by the main clock, right? Yes. So there are two requirements that you need to see. One is your network card should have nanosecond timestamp, and it also should support 802.1 AS, and it should have a running PTP stack. So so from my presentation, you would have seen that in the SDK architecture, you are able to see this particular PTP stack, which is an implementation of 802.1 AS 2020 standard. And what this guy does is just send these kind of sync message, sync follow-up message, delay request, delay response. So these are some transactions that happen between the master clock and the slave clock. And also there are transactions that would happen between the slave clock, between two slave clocks. And also there are transactions that would happen while they are going to decide who's the best master clock algorithm. So during those times, there is announce messages. Everybody announces about their capabilities. And according to the capabilities, you put it through the funnel of the BMCA algorithm, and then you finally get out the master, like who's decided as the master. Yeah. Okay. And now I will switch off the, now what I will do is I will switch off the 802.1 time aware shaper that is running on the Moxa switch, and let us see what happens to the network here. Okay. And I will stop the time synchronization as well for us to get it quickly. Okay. So let me go back to the presentation, and this is going to continue to run. We could also see what happened in previous minutes, but still. Okay. Now, coming to this slide. So if you are already an OPCUA user, you would have a question like, how should I migrate towards OPCUAFX? So we could again divide it into two parts. One is the hardware part. some parts of OPCUAFX does need hardware support, so that comes from the TSN support on the network layer. If you do have that support, then you could uh, obviously move towards your journey that I'm going to show here. But even if you do not have a supported hardware, still you could go for this. But that's again a different branch of discussion that would deviate in this webinar. So first, what you have to do is go for the implementation of UAFX controller server based on nano embedded device profile. And then you should have PubSub UDP UADP periodic fixed 2022 profile. And then UAFX automation component, asset model and functional entity concept should be implemented. And OPCA safety is an optional thing. But when you come, so why it is here is because this is to give you an overview that even safety is supported by OPCA. When you're going for development, something like a whole robot, you need safety, without which you could not ship your product. So this is very, very important, and still it's optional in certain industries and not in certain. So that's why it's optional here. And on top of it, you would need a connection manager, and you need UAFX offline descriptor. So imagine connection manager comes into the automation components and creates the functional entity with referring to its asset model. And imagine if there's a motor, the connection manager would come inside the motor and would say, start receiving your control data from this particular device with this particular PubSub, with this particular PubSub details. For example, this is the multicast address, this is the port number. Make sure you start listening to him and start moving your motors accordingly. So this is what the connection manager does in simple words, but I might be not doing justice to the full explanation. But this is a basic to it's also, this webinar is also target for beginners as well. So that's why I'm giving simple examples to understand. And for sure, you need security on all layers. And with this, you could start your journey. And whatever we saw on the graph level is our ETSN test suite. So here we have just seen the demonstration of number 2 here, the item number 2, and we did not show the other parts because this might also create a lot of confusion and questions. So we wanted to keep this concentrated to see how TSN is helping us to do IT/OT convergence and how real time is promised. And all the demonstration and all the robot demo, the motor control demo, and whatever you saw, the live demo here is part of our ETSN SDK toolkit. So ETSN is our OPCUAFX SDK, and it comes along with all the stuff that you saw in the SDK architecture. Test suite, training and support. 802. We have our own PTP stack, own LLDP stack, and also we have all the know-how that would help you to start your journey from moving towards from OPCA to OPCUAFX. Yeah, and moving on to the next slide. Okay, why ETSN is because it supports all the major TSN manufacturers. So we have a reference implementation on Renesas, on TI, Texas Instruments, STM on the device or smaller low footprint level. And also we support all Linux architectures as well. And also we support NXP. There are some other variants with STMs as well. And on the ORTAS level, it's going to be FreeRTAS, RT Linux, ThreadX, Zephyr. We have various reference implementations as well. So for people who are more interested, if you believe that this technology could help your business, you have heard about it, or how to take your first step, how to train your team, or how to do something hands-on. So we offer a 2-day hands-on workshop for OPCA PubSub over TSN, which is also obviously UAFX. So this is our overall training like training model that we have for people who wants to start their journey. So you would have a lot of questions like why this test tool, why just eight traffic classes, who defined these 8 traffic classes. I could see that there are going to be a ton of questions. And now you could see, since we switched off our switched off the traffic shape, time hour traffic shaper on the Moxa switch, now you could see that all the traffics have crumbled again. Yeah. So this is a quick demo, and at our workshop, we would be doing a lot of exercises similar to this, and I guess it would be very much interesting. Please do reach out to me, and we could discuss more about how we can proceed here. So with this, I mark my end of my webinar here, and thank you so much for Utunga for organizing this, Schneider Electric, B&R, and also BE.services for giving me this opportunity to present here. And the part 6 of this webinar is going to be on 27th February, and the topic would be OPCUAFX architecture, key concepts and insights. And part 7 is going to be on 13th March by Belden. Please stay tuned. Stay tuned with our OPCFX professionals group on LinkedIn and also on YouTube. And also, please don't forget to follow me, and I will be continuously posting insights, progress, what is happening on this ecosystem. And yeah, finally,